Yeah, it's still loading. All right. Okay, so 4.6, torque on a coil. Okay, so when you are talking about torque, now what does it mean by torque? Torque is a tendency for an object to rotate. Okay, so previously we have learned that if you have a straight conductor and you place it inside magnetic field, okay, now let's say this is your magnetic field. Your field is now entering the page. Okay, so you have a rod right here. Okay, so when you have a current flowing through it, then this rod, it will start to experience, okay, it will experience a force. Okay, a force will be acting on it. A force will make it to move. Okay, so what is the directions? Okay, what is the directions of the force? So by using your Fleming left hand rules or your right hand grip rules, where you use I cross B, okay, I going upward, B going inside, then you have a force going to the left hand side. Okay, so when you place a conductor, a straight conductor in a magnetic field, it will start to move. Then how about a coil? So if you put a coil in between magnetic field, what is going to happen right here is that the coil will start to rotate. And that is what we are going to see in 4.6, the tendency of a coil to rotate. Okay, when you switch on the power supply, when you connect it to the power supply. So what happens right here, if you look at the diagrams given, diagrams give you the north, okay, the north pole right here, the south pole, meaning that the magnetic field, okay, the magnetic field is given is from left to right, okay, and then according to the diagrams given, current is flowing in the anti-clockwise direction. Now, when it comes to a coil questions, what are you going to do? Okay, if you want to check how it's rotate, you look at the force acting on both sides, acting on the side that is perpendicular to the magnetic field. So for instance, if you look at B and the first I, okay, you look at the B here and this current. Now, current is going to the left, B is going to the right. They are parallel to each other. When they are parallel to each other, okay, theta is equals to 0 degree, meaning that force is also equals to 0 when it is on the at the upper side, okay, at the upper wire, upper coil. If you look at the lower coil, current is going to the right, B is also going to the right. Once again, angles between them is equals to 0 degree. So the force is also equals to 0. Okay, so upper part and lower part of the coil, they have no force acting on it because of the angle. Meaning that what are we going to do? We are going to focus on two sides. The side where current is perpendicular to the magnetic field. Okay, the side where current is perpendicular to the magnetic field. So now what I have right here, okay, if you look at this diagram, so according to the diagram given here, okay, the diagram at the center, it is viewing from here. You're locating your eye from at this point, okay, from the bottom part. You're viewing it from the bottom. Okay, kalau kamu tengok dari bottom, okay, you're looking from the bottom, this is what you see. So you have current I flowing towards you on the left hand side and current I into the page on the right hand side. Okay, sebab kamu tengok dari bawah. Okay, kamu tengok dari bawah. So what is going to happen now? You have current out of the page and we know B is from left to right. Okay, so what are we going to do? We are going to determine the force acting on both sides of the coil. So for a left-hand side, okay, for a left-hand side, I is out of the page. Okay, I is out of the page. B is going to the right-hand side. Okay, B is going to the right-hand side. So by using Fleming left-hand rule or your right-hand grip rule, okay, you will find that your thumb is going upward. So force is going up on the left-hand side. If you repeat it again, but now the directions of I, you change it into the page, you will see that the force is now into the page. It's now going downward. Okay, it's now going downward. So I into the page, force going downward. I out of the page, force going upward because your B is going to the right-hand side. One going up, one going down. What does it mean? It means your object is now rotate in the clockwise direction. The coil is rotating in the clockwise direction. Okay, because of the field, the directions of the field, and also the directions of the current. So if you change the directions of the current to a clockwise direction, then the coil will be rotating in the anti-clockwise direction. Okay, of course, it depends on the directions of the magnetic field. So provided the magnetic field is the same, okay, kalau sekarang saya ubah arah current, if now I change the directions of current, okay, now I'm using the same coil, but now I let the current flow in the clockwise direction. Okay, I let it flow in the clockwise direction. And then the field, I let it still coming from the left to the right. So the direction, okay, the diagram, the bottom view, if you're viewing from here, okay, the bottom view, it will be like this right now. Okay, so I on the left-hand side is into the page, and then on the right-hand side is out of the page. So the direction, okay, the directions of the force will now be, okay, this is your B, okay, your B. So the force will now be moving in the opposite direction. So now this will give you a anti-clockwise. Okay, your coil will now rotate in the anti-clockwise direction. So it depends on the directions of the current and also the directions of the magnetic field. Then you determine the directions of the force on both sides of the coil. Okay, the upper part and the lower part is not that important because the total force exert on it, okay, the total force acting on these two part is equals to 0. So it won't affect the directions of the rotation, all right? Oh yeah, there's a corrections I wanted to make in your diagram right here. Okay, force is a vector product, so it should be they should have an arrow on top of it. B is also a vector product. Okay, so you tambah arrow ya, you tambah arrow. Alright. So yang ini bow punya, bow is already representing a vector. Okay, bow punya representing vector. Okay, so if you look at this diagram, okay, if you look at this diagram, now equations given is torque equals to NI A cross B. Okay, A cross B. So by using your right-hand grip rule, the right-hand grip rule that I taught you guys in a SEM 1, chapter 1, you should be able to determine the directions of the torque. So by using your right-hand grip rule A cross B, you let your forefinger pointing towards A, and then your palm pointing towards B, facing towards B. You will see that for the diagram given, the torque is into the page. Aha. So torque, okay, torque, it doesn't represent the directions of rotation. Okay, torque, it doesn't represent the directions of rotation. It just tells you the tendency of an object to rotate. If you apply right-hand grip rule, you will see that the torque in this diagram, okay, the torque in this diagram is into the page. Okay, into the page. So 4 fingers follow the directions of your A. Your palm let it face towards directions of the B. You will see that your thumb is into the page. So that is how you use right-hand grip rule to determine the directions of the torque. Right? So that is how you determine it. Okay, so don't get confused. Directions of rotation, it doesn't represent the directions of torque. Okay, so kalau soalan minta Anda tentukan directions of torque, then you have to be careful. Okay, but directions of rotation, anti-clockwise or clockwise, depending on the directions of the force. Okay, depending on the directions of the force. Now, and once again, if you look at this equation, torque equals to NIA cross B. Okay, meaning that if you expand this equation, okay, torque equals to NIA cross B. So if you want to change it into an equation that can be used to calculate magnitude, then torque would be equals to NIAB sine theta. And this theta obviously is going to be the angle in between A and B. When it comes to determining the directions between A and B, this is the part that you have to be extra careful. The A right here, it doesn't represent surface area, okay? The vector A right here. Vector A right here, it doesn't represent the directions of the surface area. It represents a direction that is perpendicular to the surface area. That is your vector A. Okay, vector A bukan surface area punya arah, tetapi dia adalah perpendicular to the surface area. So let's say now if you put a book on top of a table, okay, kamu letak satu buku. Oops, nampaknya buku saya sengit. Okay, so if this is your book, okay, so this is a book, for example, this is a book. So this one, okay, here we say it is a surface area. Okay, this is the A, the values of A that you're going to use in your calculation. Okay, this is a the cross-sectional area. Vector A is a vector that is perpendicular to the surface area. Okay, so this is surface area, but now we're not going to use surface area. We want a vector. So vector A is perpendicular to the surface area. So make sure you don't get confused between these two things. Usually students got it wrong in top because you got the wrong angle, because you got the wrong A. Okay, surface area and vector A, they are two different things. Surface area, you just use the width times the length. Okay, but when it comes to a vector A, it is perpendicular to the surface area. So angles here, sine theta, this theta here, it represents the angle between vector A and vector B. Okay, vector A and vector B. Not between area and vector B. Okay, bukan antara area dengan B, tetapi antara vector A dengan B. So make sure you got it right. Okay, make sure you got it right. Vector A, it's very important in top. So if you got the wrong angles, then you wouldn't be able to get the right answer, right? So the wires on the side of the length are parallel to the magnetic field. Okay, this one I already explained it. I will just go through it quickly. Okay, so thus the force on the wire are zero. Force acting on the side of the length is perpendicular to the magnetic field. Therefore, the magnitude is given by F equals to ILB sine theta. So it depends on your theta. So for both sides, you have the maximum force because angle is 90 degrees between your L and B. Okay, so angle between L and B is 90 degrees. Okay, so you have maximum force on both sides of the coil. Okay, so the force on the left hand side, the force on the left in the left side. Okay, the force in the left side of the coil F1 is out of the page, or we say upward if you look at it from this view, okay, from the original diagram, while the force on the right side is into the page. Okay, this statement is given based on this diagram. Okay, based on this diagram. So if you look at it from the bottom view, then you are going to get a upward force or downward force. All right, it depends on how you sketch the diagram. So you see, again, the question, it comes back to how you sketch the diagram. That's why sketching is very important in physics, because it helps the examiner to understand your idea, to understand your view. Okay, so it depends on which diagram that you're using. If you're using the first diagram right here, okay, if you're using a diagram 1, then you will have out of the page and into the page. If you're using diagram 2, then you have upwards and downwards. Right. So since F1 is equals to F2, the total force on the coil is 0 because one up, one down. Okay. So the coil will not undergo translational displacement because net force along y-axis is equal to 0. So it will not undergo translational displacement, meaning that this whole coil, okay, it won't move up or down because the total force along the vertical axis is equal to 0. Okay, recall the things that you learned in chapter 8 last sem. Okay, that is what happened. So summations Fy is equal to 0. That is the meaning of this statement. So no translational motion. Dia tak akan bergerak secara linear. But then the coil, the torque is not equal to 0. Okay, because the force is going towards different direction, so it can rotate. So even though summations Fy is equal to 0, but summations torque is not equal to 0. So if the coil is assumed to be pivoted at point O, so that it can rotate around it, these two forces will produce a torque about O and rotates in the clockwise direction according to the situations given, according to the example given. The magnitude of the torque is given by torque equals to R cross F, the equations that you learned in Sem 1. So R is A over 2 right here. So they derive it. Okay, force is IBB. Okay, IBB, which is from here. Okay, it should be IBB. Because B is the length. Okay, it's the length of your coil. Okay, B is the length of your coil. So A over 2 equals to IBB. Okay, now you're given a coil where this is A and then this is B, the length. Okay, the length. So after you derive it, eventually you're going to obtain torque equals to IAB. All right. So if the coil makes an angle with the magnetic field, therefore the coil will now be equals to torque equals to IAB sine theta. Okay. So they're derived. Okay. They're memang ikut derivation. So area is A times B. Therefore, equation is now torque equals to IAB. So if the coil is looped with n turns, so the equations given right here, the first equation is just for one turn. If you have more than one turn, then you use NIAB sine theta in magnitude form. But in vector form, torque is equals to NI A cross B. Okay, kamu ada dua equation. One you explain in terms of vector, where you use it to determine the direction. And then another one is in the magnitude form. Okay, it's in the magnitude form where you use it to calculate the magnitude of the torque. So torque, okay, is the torque on the coil, magnetic flux density is B, I is current flow in the coil. So angle, now this is the part that I asked you to be careful just now. Angle between vector A and B, okay, vector A and B, not between A and B. Remember, A and vector A, they are two different things, okay? So A is area, surface area. So in calculations, you use the values of surface area, but when determines the direction, you use vector A. Okay, this is vector A, vector area, and it is not surface area. Okay, it is not surface area, but indeed is perpendicular. Okay, perpendicular to surface area. Right, perpendicular to surface area. So that is what happens in torque. So magnitudes of torque in a radial field. Okay, so radial field means that the field is a curve. Okay, it's a circle. Okay, it's a circle. So radial magnetic field, usually where can you find it? You'll find it in your galvanometer. All right, so in a galvanometer, you will have two pieces of magnet as shown in the diagram. It's exactly look like this. Okay, your galvanometer. Galvanometer. So it doesn't matter how you rotate it, you will always have a maximum field that the angles makes a 90 degree with the coil. Okay, because the coil is a radial, it's a circle, radial magnetic field. So it doesn't matter how you turn it, the maximum field, okay, the maximum field, it doesn't matter what position the coil is in, we always find the plane of the coil that is perpendicular to the field. So it will always experience maximum torque. Okay, so tak kisah macam mana kamu turn. Okay, there must be a torque, there must be an angle that is always perpendicular to the coil. Okay, perpendicular to coil. So when the current I flow in the coil in the radial field, the torque produced by the current will be torque equals to NIAB sine 90 degree. Okay, this is if you have a radial magnetic field. Okay, ini cuma valid kalau kamu ada radial magnetic field. So it will always give you 90 degree. Okay, you will have a lot of degree, of course, because it's a radial. The magnetic field is coming in all direction. Okay, the magnetic field is in all direction. Here, here, here. But one of them, they will give you 90 degree, and that is the maximum values that we want. Okay, that is the maximum values that we want. So in other words, the magnitude of the torque remain the same even if the coil has rotated about the axis through any angle. So it is unlike where you have a parallel magnetic field. Okay, if you have parallel magnetic field, then the values of the torque will keep changing. Okay, kalau kamu ada parallel magnetic field, okay, so when coil rotate, the torque changes. Okay, torque changes. But if you have radial magnetic field, the magnitude of the torque remain the same. Okay, even if it is rotated. So this is just for radial magnetic field. All right, so make sure you don't get confused. Okay, make sure you don't get confused. Usually in calculations type questions, we will give you parallel magnetic field type questions, but in the explanation questions, okay, usually they like to ask you the radial magnetic field. They like to use radial magnetic field. Why? Because this one, it can be applied in galvanometer, and that is part of your syllabus, which is in the next page. The next page, it asks you to explain the working principle of a moving coil galvanometer. So moving coil galvanometer use the principle of the torque on the coil in radial magnetic field. Okay, therefore the angle is always equals to 90 degrees. So this is exactly what happened in a galvanometer. Okay, galvanometer. So right now we don't have a face-to-face class. That's why I cannot show you the actual product. But you try to search online. I believe there are plenty of the picture, okay, in online. So you have two pieces of magnet, okay, permanent magnet on both sides. And then in between them, there is a piece of soft iron core. Okay, yang tengah-tengah punya cylinder, that is soft iron core. Then you have a spring on top of it. Okay, ada spring di sini. This is actually the spring. Okay, this is the spring. And then at the bottom, there's also a spring. Okay, so you have a spring on top and at the bottom. And then you have a pointer. Okay, at the pointer, this pointer is being attached to the spring. All right, and then this black color straight line, this is the coil. Okay, this black color line, this is the coil. Oops, coil. All right, so it consists of a coil of wires suspended in the magnetic field of a permanent magnet. The coil is rectangular shape and consists of many turns of a fine wire as shown in the figure. Okay, when current flow through the coil, the magnetic field will exert a torque on the coil. Okay, so this coil, okay, this coil, it will experience a torque. Okay, it will experience a torque and makes it rotate. The values of the torque is given by torque equals to NIAB. Okay, so, well, of course, there must be something to stop the pointer from keep rotating. Otherwise, how are you going to obtain a reading, right? So the things that stop it from rotating is the torque that is opposed and being generated by the spring. That's why I told you just now, the pointer is being attached to a spring. Okay, so the pointer is being attached to a spring. When current flow through the coil, this coil, it will rotate. But then because of the spring, okay, spring exert a torque in the opposite direction, where the torque is given by torque equals to K theta. Okay, so when torque generated by magnetic field is equal to the torque generated by spring, then the pointer, the needle will stop. And that gives you the reading on galvanometer. Okay, that gives you the reading on galvanometer. So there are two torque being generated in this diagram. One is being generated by the coil. Okay, coil gives you a torque from magnetic field. Okay, torque from magnetic field. And then spring, they give you a torque, okay, in the opposite direction. Okay, in the opposite direction. So torque S and torque. When two of them, they are equal, pointer will stop. Okay, so when it is balanced, we say torque equals to torque S. Okay, so this is just an additional information for you. Okay, you don't have to know how to calculate it. Okay, just that you have to know torque is proportional to angles and I is proportional to angle. Therefore, when you have a larger current flowing through the galvanometer, the readings of the pointer will be larger. Okay, it gives you a larger reading. Larger current gives you larger reading because angles is proportional to current according to the equations derived right here. And of course, remember, this is not in your syllabus. Okay, this is just give you an idea on what is the relationship between the angles and also the current. Right? So from the equations above, we know that torque is proportional to theta, and thus I is proportional to theta. So when your I increase, theta increase. Therefore, it gives you larger reading. Okay, larger reading on galvanometer. Right? So this one, you just have to know a brief idea, especially in terms of these two torque and what happens in a galvanometer. Okay, so you don't have to know the calculation. You just need to know how it works. Okay, now last page, last subtopic, applications of a motion charged particles. So where can we use the moving charge, okay, particles in a magnetic field? So explain the motion of a moving charge particle in magnetic field and electric field for V, B, and E perpendicular to each other, and use velocity in a velocity selector. Okay, velocity selector, we will discuss it in chapter 11. Right now, you just have to know how to calculate the values of V, velocity. So consider a positively charged particle with mass m and charge q and velocity enters a region of a space where it contains both electric and magnetic field as shown in the diagram. Okay, and they are all perpendicular to the velocity. So you have E, you have B, and you have V at the same time. Particles enters with an initial velocity. And what is important right here is FB and FE. Both of them, they must be pointing towards opposite direction. Okay, in order for this particle to move in a straight line. If they are both pointing towards same direction, then this charge, it will be deflected towards either plate. Depends on the direction of the force. But in a velocity selector, we want it to move in a straight line. Okay, we use this one to control, to manipulate the path and to accelerate the charged particles. Okay, to accelerate the charged particles. So the charged particle will experience the electric force downwards according to the equation to the diagram given. Fe is downwards with a magnitude QE, and Fb is upward with magnitude QVB. All right, as shown in the figure. And if the particle is moved in a straight line, we can then say Fe equals to Fb. Okay, so QVB sine 90 degree equals to QE. Rearranging equations, you will obtain V equals to E over B. It gives you the velocity of the charged particle. Okay, by knowing the strength of electric field and the strength of magnetic field, you'll be able to identify the speed, the velocity of these charged particles. So only the particles with velocity equals to E divided by B can pass through without being deflected. Okay, because if FB is not equals to FE, then V is not equals to E divided by B. Okay, so only particle, this is a condition. In order for it to move without being deflected, okay, the velocity must be equals to electric field strength divided by magnetic field strength. All right. So if, okay, I'm going to just write it right here. If you want to write it down, of course you can. If FB is not equals to FE, then V is not equals to E over B. So particles will be deflected. Okay, particles will be deflected to either plate. So velocity selector normally used in mass spectrometer. Mass spectrometer is an analytical technique that measures the mass to charge ratio of the ion. Okay, so this spectra can identify an unknown compound. So mass spectrometer, we use it to identify an unknown compound. Okay, measure the abundance of elemental isotope and find something out about the structure of the large and complex molecule. Okay, so what is happening right here? Now, you use a mass spectrometer. Okay, now you shoot an electron. Usually this is here has a gun, okay, a particle gun that shoot the electrons or charged particle out. So it shoots a particle out from the gun. Particle will move with an initial velocity, and it passes through this path. Okay, it will move in a straight line and make sure that it enters the hole right here. As it enters the hole right here, this region is now, okay, is now filled with just a magnetic field without electric field. Okay, so here is B plus E, but when it enters this zone, you have only magnetic field. So when it's being deflected into a region with just magnetic field, okay, recall the things that you learned in a previous subtopic. When you have moving charged particle in magnetic field, it will start to move in a circular path. Okay, it will start to move in a circular path. As it moves in a circular path, you can then identify the radius of the particles. So from here, the scientists, they are able to determine what type of particle is being generated right here. Okay, based on the mass of the charge, and then based on the radius. Okay, based on the radius measure right here, they will be able to identify the type of the particle. Okay, so that is the mass spectrometer to identify unknown compound. So should it enters a region here, So the information produced in this region, the semicircular path generated by this ion, these particles, okay, will then be used to identify, okay, to identify the type of particles. Okay, so that marks the end of chapter 4. Okay, chapter 4 just give you a brief idea. We will discuss all this again in chapter 11. Okay, the introductions to particles. All right, so here is just a brief introduction, just to let you know how to determine V, okay, velocity, and how to calculate the R, okay, how to calculate the R as a moving charge particle entering a region with magnetic field. Okay, so nanti semua ini memang kita akan tengok sekali lagi di chapter 11. Alright, so jangan risau. Right now, yang penting Anda kena tahu pengiraan. Chapter 11 kita akan tengok semua teori. Okay, kita akan tengok teori macam mana kita tentukan semua benda ini. Chapter 4 untuk Anda buat pengiraan. Macam mana nak kira velocity, macam mana nak kira radius and so on. Alright. So that marks the end of chapter 4. Okay, and now it's 11:45. I think I will stop right here. Okay, I will continue chapter 5 next week.